Hello. Today we'll be looking at the momentum equations or the so-called Navier-Stokes equations for fluids. We're deriving it. Previous video we derived the continuity equations. So right now we're doing the Navier-Stokes equations. So what are the Navier-Stokes equations? These are the equations that tell you the evolution of fluid body due to forces the fluid experiences. And it's basically Newton's law of motion written for fluid elements on a per volume basis. So here in the top right, we have Newton's law, normal, well-known F equals to ma. Now, for the forces that will act on such a fluid element, they are divided into surface forces and body forces. Now we have such a fluid element in this diagram here. Here's such a fluid element, an infinitesimal fluid cube. So what are surface forces? Surface forces are forces that act only on the faces of these elements. But body forces act on the volume. So surface forces act on areas, body forces act on volume. An example of a body force is the weight, that's gravity. So that's why I wrote G, but it could be anything. If you get into the fluid in the field of other fields, say field called magnetohydrodynamics, you could have a body force due to the magnetic force on the parcel of fluid. But now the only body force we see is gravity. For the surface force, we have viscous stresses, we have pressure forces, and the likes. But the only one we have now in motion is viscous stresses and pressure forces. Now our acceleration here is the substantial derivative of the velocity, which is total dv dt, following the fluid particle. And then our body force, I split into its components, gx, gy, gz. Now for gravity, we know only the gy acts in the j oops, no, for gravity is the gz, so gravity points in the z direction. Or here we have the vertical direction being y, so it will be the y direction, whatever. It just depends on your convention. So gyg plus gjk. So how do we do this? We sum forces in one direction and we equate it to the accelerations. And then we'll also try to write constitutive equations, that is, putting the stresses in terms of strain. So let's do this. So an example now will be take the x direction, for example. Look at this diagram. Here's a fluid element, and we could see that there are forces in on each face, but then they all point in the x direction. And now what would determine the motion of this would be the sum total of the forces. So on this phase, an example now how we read this. On this phase, we have the pressure force acting is P, acting on the face of area dy dz, and then at the distance dx, the pressure acting on this face is P plus dp dx. So this is like a Taylor series expansion for P around this first point, where we neglect higher order terms. So now the total, the resultant force due to pressure alone will be what? P minus P plus dp dx. And why it is the initial minus the final, it's supposed to be the final minus the initial, but the pressure points inward as opposed to other forces which point outward from the area. So there's a minus sign here. Then this will be minus P minus P. So this is plus P minus P plus the P dx. The same for the shear stresses. Here at this phase, you have tau xx dy dx. Then at this phase, you have tau xx plus d tau xx dx. So that's just the change in the normal shear stress the normal stress on the element as you moved the distance dx. So same for the tau yx and tau zx. So what happens when we what happens when we what happens when we simplify this is that the the absolute values at that point cancel. That is p cancels p, tau x is constant, and what we are left with is the derivatives of the stresses. So the resultant force is minus the p dx times the volume minus the tau x dx times the volume. Then the total force in the x direction per unit volume becomes this, because the unit volume is dx dy dz. The volume is dx dy dz. So we divide it out and then we have this. We're left with this. So that means this is the forces. And then using our F equal to ma, we equate this towards the accelerations. The mass times acceleration equals this. So this is basically a statement of Newton's law for fluids. So what would take you from Newton to Navier-Stokes would be, one, expressing this stress terms in terms of velocity gradients, instead of deformations or rates of deformations. Now, the relation we have for that is called Newton's law of viscosity, which he stated for Newtonian fluids, where you have, for Newton's law of viscosity, the shear stress is proportional to the rate of shear strain. Now here we have shear stresses. Here we have shear stresses, and then they are proportional to what? The rate of shear strain, where the constant is the viscosity. So the constant here, mu, is the viscosity. And then we also have an expression for normal stresses, and this is due to Stokes. So Stokes also wrote these constitutive equations. Here we have tau x is equal to lambda times the divergence of V plus 2 mu du dx. Now, where lambda is the second coefficient of viscosity, lambda is known as the second coefficient of viscosity, and lambda is usually given as minus 2 over 3 mu. So this is called Stokes hypothesis. Stokes hypothesis. So putting all this together, we could see that we've expressed the stresses in terms of the velocity gradient completely. So we could put that back into the equation. And then when we put that back into the equation, we arrive at this. So when we have tau xx, we substitute this. Tau xy, we substitute this. Tau xz, we substitute this. So just for the x direction, this is what we need: 1, 2, and 3. And then we have this. Now, I'm just doing the x direction, but if you want to do other directions, you could see that it's the same thing if you follow the approach that I've been using. So now I would quite show some intricacies in what I've done to kind of simplify this further. So while substituting this, I moved the dx out. I expanded this. So the reason why I wanted to expand this was to bring this in a form that's the most used form for the Navier-Stokes equation. Then by expanding this further, I split this 2 mu du dx into each 1 mu du dx into 2. So after having that, we went down to this. If you could look closely, then I have this, which is, you could notice that it looks familiar. This is the Laplacian of u. So I split this into the Laplacian of u, and that relates to the viscosity. That is actually, I could call that a diffusion term of velocity due to viscosity. So now, once I did this, and now another intricacy was that I commuted the derivatives here. So it's nice to know that these derivatives in general are not equal. So in general, you don't have d dy of d dx, let's say phi, equal to d dx the phi, the y. But now in special cases and in most physical cases, dealing with continuous partial derivatives, they actually commute. So you could move this, you could move this to the other side, you could switch this. Now, when you switch this, you have this interesting term, mu du dx, mu d dx of du dx plus dv dy plus, which is the divergence of v. And then we bring it down here, we have minus dp dx plus lambda d dx divergence of v plus mu d dx divergence of v plus gx. Now, recall from Stokes hypothesis, we took this lambda to be equal to minus 2 over 3 mu. So if we put lambda equal to minus 2 over 3 mu here, we'd have this rho du dt is equal to minus d rho dx plus 1 over 3 mu d dx divergence of b plus mu lambda square u plus gx. So this was the full equation, full momentum equation in the x direction. But now I want to extend this to all directions. So what do? Since this is just a component in the x direction, we could write an I here and then write the same thing for the j direction, y direction, and write j. And for the z direction, write k. And so in general, we could then use the properties of vector notation to show that one, du dt plus dv dt plus dw dt I jk is a general, a vector, which is what? Rho dv dt, big V, capital V. Then minus the rho dx I minus 0 dy j minus 0 the gk is what? The expression of the gradient of the pressure. This is minus grad p plus mu d this dx d dy d dz is what? The gradient also of the divergence of v plus mu the del square ui is also a vector, which is mu del square v, the vector. Then gx, gy, gz in general was g, which was a body force. Now we could divide this by the density, and then we have this expression here, where the dynamic viscosity now turns into the kinematic viscosity, nu. Then thus we have the general form of Navier-Stokes equation, which is what? The v dt plus v dot grad v is equal to minus 1 over rho grad p plus 1 over 3 v grad divergence of v plus nu grad square v plus g. So that's the general form of Navier-Stokes equation for any situation: compressible fluids, compressible Newtonian fluids subject to both surface forces and body forces. Now, there are special cases which you always see. Whenever you look up the Navier-Stokes equation on the internet, you actually see a more reduced form than this. Those are usually simplified. An example is the most incompressible version, for which we know that what? The divergence of V for incompressible fluids is equal to 0. So we could get rid of this term here. And then we have this, a general term which you always see, which is what? The V dt plus V dot grad V is equal to minus 1 over rho grad P plus nu divergence square V plus G. So now, let us we could just mentally verify this equation. You could see that the acceleration on this side is equal to the forces on this side. And we will see the action of each. This tells you that what? A pressure gradient, not an absolute, not a general absolute pressure. The gradient of the pressure is what matters to what make the flow move. So when you have a change in pressure, a change pressure gradient over a distance, it exerts a pressure force on the fluid to make it move. Then this also, the diffusion term, this tells you about the diffusion or the degradation of velocity due to the action of viscosity. So wherever you have places of higher viscosity, higher velocity than its neighbors, This term would help to diffuse it due to the action of viscosity, and that would help to what? Change the velocity. Then also we have what? We have the body for which is gravity. So on the action of gravity, this will help. This will actually act to move the fluid. If there are no body force, if you neglect it, so there would be no motion due to body forces. So this in general is an Navier-Stokes equation. I hope you enjoy the video. If there are any avenues you want me to improve upon, I will be welcome to. That would be welcome. I would like to hear that. Thank you.